Hello everybody, this is Alex, and in today's video I'll be using the SnowFlake cloud database, and I'll be looking at some stocks data. And what we'll do today is create very simple linear regression model and a naive Bayes uh, categorical classifier to try and make some very basic predictions on our data and see how that compares to the average stock market returns. And this is just for fun and to start exploring what we can do with the data and how we can do this in Snowflake. So the first thing that I did is I created this table, and I have the symbol and the dates. These would be the primary keys of my table or unique row identifier. I have the high low for the day, the average price the stock was traded, the volume average that was traded in dollars, and this is adjusted for historical stocks. And I have some previous days, which are just lagging days. This will help us join the data later. And I had already pre-calculated some simple moving averages that we'll be using for our model. So this is a very simple approach, and it's worth exploring as a good starting place. I loaded the data from my S3 bucket, and I had already deleted it, so the credentials are no longer relevant. So if we take a look at our data, we'll use Apple as an example. And I just ran this query, so it should be already cached. And I'm using an extra small compute warehouse in Snowflake. I'm still on the trial edition here with this account. So here's some of the data that we can take a look at. We can see that the data starts at about 2000, and we can confirm that just by running this query. We want to know the total number of rows, number of symbols that we have in our data, and what is the min and max dates of our data. So we have 19 million rows in this data set, about 7,700 unique symbols, and we have data going back from 2000 to 2024, so about 24 years of US stocks data that are on the NASDAQ and the New York Stock Exchange, a total of 7,700 of them. So the first thing that I'll do is I'll create this view. So we want to make a prediction into the future, and we want to use historical data to see how that makes our prediction relevant. So if we look in the from clause, I'm selecting from our table, and I'm joining into the future here with T for tomorrow, N for now, and Y for yesterday. So I'm looking where tomorrow's date is the lagging date of today, and yesterday's date is the opposite. The lagging date of today is yesterday's date. So I want to know, so I have Y for yesterday, T for tomorrow. So I'm looking at a symbol on a specific date at a specific average price that I can buy that symbol. I'm looking at what was the volume in dollars yesterday that it was traded in. Looking at tomorrow's price, right? And I'll need that here for the prediction. The prediction will be, is tomorrow's price greater than today's price? And this would be a Boolean, true or false. Is the price up or down? And then the ratio between the two. If we take tomorrow's price divided by today's price, what is the price change on average? Greater than 1 will be positive, less than 1 will be negative. And here we have the different features. So for the regression model, we'll use the simple moving averages as a ratio of the yesterday's price, because we may not know the complete average price of today until the day is done. So we'll be only looking at yesterday's data to make a prediction about tomorrow's price. And of course, our model might be better if we had more information about today's price as it's moving along, but we don't want to make any mistakes of having any kind of forward-looking indicators in our models, because that might make them perform better than they actually would. So we always have to be careful that we're only looking at data that could actually be available to us in real time to predict future data. And here for the categorical features, this would be for the naive Bayes. It would be, is the price, for example, the moving average price less than the average yesterday's price? And then I have these other combinations where I'm comparing the moving averages between themselves. So I've essentially expanded this combinatorially out of the 4 features. So this is the view of our data. So I had already created it. I can go ahead and run this again just to show. Okay, let's run. Okay, and let's run a sample query. Take a look at our view. Okay, so we have some symbols here. Their average price, the volume. This will be the previous day's volume. The moving averages as a percentage, or rather ratio, or percentage plus 1 change. And then the categorical features, true, false, and then the future predictions. Did it go up or down in the future? And we see true because it's greater than 1. Anything that less than 1 would be false. Okay, so before we proceed further, well, let's get a baseline statistic. Let's take a look at what our data is showing as a baseline for what is the likelihood a stock will go up or down. And I had already pre-calculated some of this. So if we take a look at the total rows of 19 million and the average time that the price went up would be 9,500,000, so about 50.267%. Now for our model, and here is the notebook that I created, I did exclude certain anomalies in the data. I don't want anything that went up more than 2-fold in a day or dropped more than 90%. And the reason for this is because our linear regression model will not work as well with anomalies, because remember, linear regression is a squared sum, and so the further the anomaly is deviated from the mean, the more weighting it will receive in a linear regression model, and it could skew our results. There are other interesting models that we can use for analyzing black swan events, but for this model we will need to exclude them in order for it to work best for an average day's return. Okay, and so let's take a look at the new numbers now. If we added those filters, I don't expect them to be too different. And only a small set of data got filtered out, as we can see. And the results are almost the same. If we filter out the anomalies, we're looking at 50.260 probability that a stock will go up on an average day, an average stock. Like that. Okay, so let's get back into our notebook and let's load the data. So I will load some of our libraries here, and I will load the data from our view into cell 2, and this should be fairly quick, even with an extra small warehouse. This whole notebook typically runs in a couple minutes, which is pretty good considering we're processing 19 million rows of data. Okay, there we go. We have the data loaded in 28 seconds. So let's separate the data now. We have our categorical features and our regression features, our categorical prediction, and our regression prediction. We will load cell 2 into a pandas data frame, and we will create a training and a test subset. I will train the data on everything below 2022, and I'll try to predict everything in 2022 and above. And I will separate the data into training and test for both regression and categorical features. So let me kick this off. It'll probably run in about 36 seconds or so. And this, of course, is happening all in memory of the extra small warehouse. So we have to make sure that our data can fit into memory. Okay, while that's running, I will go over here, and here we will import the naive Bayes categorical classifier, and we will fit the data, and instead of having the prediction be a category true false, we will get the probability, which is a little bit better to play around with because you can have some probabilities be more confident than others. Okay, it's good that that cell is loaded, and I can see here cell 3 is loaded. I will move to cell 4, and I will run the naive Bayes model. And what the naive Bayes model does is essentially says, well, what is the based on historical data, if say the moving average 5 days is less than the moving average 15 days and greater than the moving average 30 days, what is the likelihood out of all those days that the stock went up, essentially? And it's looking at all those combinations. So here's the probabilities that it got out for our data for all the rows that we have. This is for 2022 and above, and here I printed some of the log probabilities stored in the model, and the reason they're negative is because you have to take them to the exponent, right? Because the negative values, the way you want to multiply probabilities is you add them in the log form. That works much better than having to do multiplication, and that way you don't have floating point precision issues. So here's our linear regression model. It's much more simple. We have the 4 features, and we see that there is a negative relationship with the simple moving averages, 5 and 15, a positive one for 30 and a negative one for 60. Okay, so this is essentially saying that the higher up the moving average is, the more likely the stock will go down. So there is some reversion to the mean happening on average, and there's maybe some sort of trending happening within the 30 days, and again some sort of reversion to the mean happening at the 60-day moving average. And of course this is not true for all stocks. We're just looking at averages here. And let's take the results of our models. We'll take our outputs and we'll concatenate them with our attribute data that we can now start taking a look in the table. So let's do that. And here we have our output data. We have a symbol for that date. What is the probability that it will go up, and what is the linear regression saying? What is the percentage that it will go up by? Okay, and then I can output the data to this table, which I already have. So let's go back and take a look here. So this is my table. I'm all data results, cat 1 results. And let's take a look at some of the sample data. So here we have the symbol, the date, the price that it was trading on today, the price that on average that it's traded on tomorrow, the average volume that it traded yesterday, and here's our predictions. The naive Bayes prediction results, probability, and the linear prediction results. And this, I think, came out of our attributes. So this is, I think this is the real value. So this is the correct classifier. It's false, but their prediction would say that it would have gone up. So here we have a mismatch, for example. So I want to take a look only at stocks with volume greater than $10 million. And that's because they're much easier to trade and enter positions, and amongst other reasons. And for the purposes of this video, that's what I'll focus on. And so I want to get some baseline numbers for the years 2022 to 2024 in our results. And of course there were some bear markets happening then, so we actually see that the average price change is less than 1. So stocks on average have gone down within those years, and this is out of all the 7,700 stocks, right? We're not looking at the S&P 500 index here. We're not looking at the top 500 most valuable companies in the market. This is for the entire market as a whole. And so the probability that a stock went up, though, and this is sort of interesting, out of the total rows that we have, which I already have the numbers here, created, yeah, this looks like the same. The probability, though, that a stock went up is actually above 50%. And this is sort of interesting. That means that an average stock will go up, but on average stocks went down. So that means the magnitude, when they go down more than they go up for these years anyways. And anything that's above this volume, which isn't that high of a volume actually for a lot of stocks in the market, considering some stocks are being traded at very high volumes, such as in the S&P 500. So let's start taking a look at some of our predictions. Let's look at the naive Bayes, and let's see if we can improve these numbers. So I already had run this query ahead of time, and so if we take a look at everything that has more than 51% likelihood of going up, we see that our average price change actually becomes positive. So we're found an edge here out of the market, and the average price going up has actually increased from 50.6% to 50.7%. So we have a small edge also in the likelihood that it goes up. What we can do now is combine our linear regression. Well, let's take a look at linear regression by itself. Let's take a look at what our linear regression predictions look like, and then we'll combine both of them. So the average price change, if we're looking at positive linear regression, is indeed positive by a very small edge. That would be 2%, 0.2, so it would be like 2 basis points, 0.02% change on average. And then if we further add the naive Bayes classification, we actually move that number up to 0.07% on average change within these years. So that's really good. That's much better than the average. And let's take a look at now what our portfolio might look like. So here's the query for running the data as a portfolio. So the first thing that I want to do is take the future price divided by the current price and subtract 1. This will give us a negative number if the percent went down and a positive if it went up. And I want to multiply it by the amount of the portfolio allocation that we would give to a single position. And let's say it would be 0.5%. And we'll see sort of why I picked that number later. We then sum up all of our positions for the day, and then we want to add a 1 back in. And the reason we want to do that is because we want to take a natural log of our percentages plus 1. What this will allow us to do is then take a running sum of our logs. And that is essentially the same thing as multiplying our portfolio percentage changes for every day. And we get a rolling multiplicative sum, essentially, of our portfolio as it's changing, because we're assuming every day we're using our new portfolio amount to place the trades. So I'll run this query, and I think the results will start to make sense once I run it. Okay. Oh yeah, and of course we have to have our filters in place. We're looking for anything that matches our criteria for our models. And we have the number of trades placed on the day, capital used, and we have here the running sum. So 0.24 would mean that our portfolio went up by 24% since 2022. Yeah, so 0 would mean break even. We can always add a 1 at the end if we want to see it 1 plus 20, 1.24. That would be the ratio change. So we can see this in our chart, and we want to take a look at a line chart, and we want to take a look at not the daily profit and loss, but the running sum, and we want to look at the date. No. Okay, let's take a look here. So the x-axis needs to be the date, and the y-axis needs to be the running sum. There we go. So this is our portfolio. So if we start at 0 in January 2022, we see that there's some drawdown here by about 10-15%, 14%, and then we see it going up and finishing at about 20-24%. And if we compare that to the S&P 500 or the SPY index, we can see that in 2022 the S&P did not break even up until around December 2023, and then it went up about 20%. So this portfolio breaks even before December 2023, actually in November 2022, and by December it's actually up about 17%. There's some drawdown here, but it's still net up 5%. So this in some sense performs a little bit better than the market. We have a bit of an edge. Let's just back down. There we go. So let's keep further analyzing our data. So we got our portfolio running. So the next question is, what are our most commonly traded symbols? And we can simply take a look at the number of trades each symbol received, And let's take a look at the results. And these are the most commonly traded stocks. I don't recognize some of them, or there's Alibaba. Oh, there's SnowFlake, I think. D-Dog. Lulu, probably Lululemon, I don't know. I think I saw Nike. So it's quite interesting. It's finding these interesting stocks that seem like they actually respond to some sort of patterns and moving averages. We can make a chart so we can actually see the distribution of these stocks, and let's make the x-axis be the number of trades, and we'll make the y-axis the symbol. And oh no, let's do the opposite. We want the x-axis to be the number of trades, the y-axis to be the symbol. And then I think what we want is we want it sorted. Order by bar size. Yes. So we can see this sort of distribution. Will WBA being traded the most frequently, and then some stocks being traded less frequently. So it looks like these ones seem to respond most to moving average patterns, at least as far as our models think. And the next thing that we want to take a look at is how much does our portfolio correlate with the overall market. So what I have here is I have the SPY data, and I'm simply joining to it from our portfolio to our date, and I save the portfolio in a table in ML portfolio 1. And so now what I can do is create a quick scatter plot, and I want to take a look at so this is the change in our portfolio and the change in the S&P 500. You can see there's quite a bit of correlation. You could almost draw a line over here, and here we can see it a little bit better. And we can definitely see on average as the S&P goes up, so does our portfolios. The S&P goes down, so does our portfolio. And if we were to put a number on this, we could take the R squared if we drew a regression line through here, and we can do that numerically here through this query. And what we get is that our portfolio has about a 54% correlation coefficient with the overall S&P 500, which sort of works as a proxy for the overall market in terms of correlation anyways. So I wanted to conclude this video. I also wanted to emphasize that the linear regression, naive Bayes are not advanced machine learning models. In fact, they're really classical statistics. They have been around for a long time. You could almost calculate them using pencil and paper. Of course, for 19 million rows of data, it would be not trivial. But they're very simple, and they're very powerful, and they're much less prone to overfitting, and they're really good general models to start with when exploring the data. So thank you so much for watching. I hope you enjoyed it. Take care. Bye-bye.